This is Professor Ricardo Jimenez. Today we will see the topic of linear monostables, and this topic will be taken from my book, the Digital Electronics Notebook, Digital Logic Practices with CMOS Chips, which will be published very soon. Okay, so we're gonna see this topic, the linear monostable. Okay, linear monostables is a topic that covers many types of digital circuits. In this case, we are designing a monostable. Let me adjust the illumination. Okay, we will design a monostable using these NAND gates. Okay, using the Schmitt triggered NAND gates HC132 and doing a set and reset function, and we will use a constant current source. That's why this monostable is linear. So let's start with the description, and where it says that the linear monostable in figure 14, because this is practice number 14 from my book, charges the capacitor CX with a constant current source formed by a PNP transistor and its associated resistors. When not Q is equal to 1, the NPN transistor, in this case, is the PNP transistor is in saturation and keeps the capacitor CX grounded to 0.1 volts. So this is what we see here. I want to show you the timing diagram at the same time. So right here, when you start the circuit, and yes, right there, you can see N3. Yeah. In this circuit, you can see that when the push button is open, you have a high logic right there. And because you have a 1 here, there will be a 1 in the NOT Q. So this NPN transistor is in saturation. And thanks to that, it is in short circuit. So it is grounding this capacitor CX. Okay. So the constant current will be getting applied to this CX, but it'll never be charged. So because the current goes directly to ground, okay, because of this short circuit. So this is the initial logic, the initial starting point, where Q is 0, not Q is equal to 1, and the circuit stays there. So you can see here BCX is not charging the capacitor on this the voltage in the capacitor CX, and N3, this gate is equal to 1. Okay, the output is equal to 1, because if you have 0 volts here, the output is 1. Now when you press the push button or the trigger for this latch, set reset latch, when you apply a 0 right there, Q will be Q naught will be 0 and Q will be 1. So and Q naught will be equal to 0, and because 0 is 0, the transistor will be in cutoff, so it'll be open. Now the constant current IK will be flowing across the capacitor, and the capacitor will start charging, as you can see here, in a ramp, in this voltage ramp, which is not logarithmic, it is a ramp. And thanks because the NOT Q is 0 and NOT Q is equal to 1, when you press the push button, it is charging because this one is open. So when the capacitor reaches the voltage that the Schmitt trigger needs to change the state, in this case is 3 volts for the Schmitt trigger 74HC132. So when the capacitor reaches 3 volts, it detects a logic 1. So this one detects here a logic 0, and then you have a logic 1 here, a 0 here, and because Q naught is not equal to 1, this changes, okay, this saturates the transistor and goes to saturation and discharge the capacitor. That's why the capacitor is right there, discharge from 3 volts to 0 volts. I always say 0.1 or 0.01 because this is because there is a voltage drop from the collector emitter, so it is not ideally is equal to 0, but in the real world it is equal to 0.1, the VCE. Okay, and so you might consider 0.1 if you wish in the equation. And anyway, the formula, the equation for the charging equation is this: the constant current is equal to VDD minus VB minus base emitter voltage divided by RE. And time is equal to RC, so we know R is equal to the power source divided by the constant current times CX, times BT plus. BT plus is the threshold voltage for the NAND gate because that will be the maximum range the capacitor will reach. And so we substitute the constant current here, we get finally this equation. Of course, I'm considering the collector emitter, we can say parasitic voltage. So this is the timing for this monostable. And so it is a good experiment for the student to test it, and that way you prove that the NAND gate has a positive threshold voltage. Okay, it might vary depending on this on the brand of the technology that you're using here. It might be a 4093 HC132, and it also depends on the temperature. You have to check the data sheet to determine at what temperature you are testing this circuit. Okay, and another application of this is the capacitance to pulse train converter using a linear charging circuit. So, and this will be the topic of my next video. Okay, thank you.